Now that we understand what the gradient of the loss means, we can take a look at a typical training loop for a neural network using gradient descent. So to train a network, we first initialize the weights and biases for all layers to random values. Next, we cycle through every training example. For each example, we first execute a forward pass, determining the output and its corresponding loss. After evaluating all training samples, we initiate the backward pass to calculate the gradient, which, remember, tells us the influence of each parameter on the loss. We then take a step in the opposite direction of the gradient. That is, we update every single parameter of every single neuron by shifting it in the direction opposite to its derivative. This is called backpropagation. We continue this until the loss converges. That is, it stabilizes or reaches a value where it no longer significantly decreases, indicating that the network has learned the optimal weights and biases to best approximate the desired output for the given training data. A key parameter during training is called learning rate. When we perform backpropagation, we want the updates to the weights to be small, so we don't just use the derivatives, but we scale them down by multiplying them with a learning rate, which is a small positive value. The learning rate determines the size of the steps we take towards minimizing the loss. A smaller learning rate means smaller, more precise updates, but may require more iterations to converge. Conversely, a larger learning rate can lead to faster convergence, but if it's too large, it might overshoot the minimum or even diverge. Choosing an appropriate learning rate is crucial as it influences the speed and stability of the learning process. A single pass over the entire set of training data is called an epoch. We will generally train a network for many epochs, making multiple passes over the entire training dataset. We'll now look at different approaches to updating the weights within an epoch. The approach we described so far is called full batch update. The entire training set is used to compute the gradient and update the model's weights all in a single step. This means that for each epoch, there is only one weight update. This tries to correct the error at all of these training data points, all at the same time. The advantage of this method is that it provides a clear and stable path towards minimizing the loss, as it's less susceptible to the noisy gradients that can occur with smaller sample sizes. However, the downside is its inefficiency with larger data sets. Processing the entire dataset can be computationally intensive and slow, especially when using deep neural networks or when the dataset is very large and has millions or billions of data points. Moreover, full batch updates might not be feasible if the dataset cannot fit in memory. The opposite approach is called incremental update. Here we will adjust the network parameters after processing each individual training example. This means that each individual update to the network will be smaller, except now, instead of making just a single update after processing all training points, we would have made many updates to the function within a training epoch, one after each example. With incremental updates, we don't want to process all data instances in the same order for every epoch, as this can sometimes lead to repetitive patterns in updates that could cancel each other. To avoid this, we shuffle our data and pick instances randomly. This method of random selection and update helps prevent cyclic update patterns and is known as stochastic gradient descent, with stochastic referring to the random selection of training instances. The frequent updates of stochastic gradient descent introduce a lot of noise into the learning process, which means it may take longer to converge to a solution and the path to convergence can appear erratic. On the upside, stochastic gradient descent often leads to more robust solutions. Mini-batch gradient descent strikes a balance between full batch and incremental updates. Instead of using the entire dataset or a single instance, mini-batch updates use a subset of training data to compute the gradient and update the weights. The size of this subset, the mini-batch, can vary, but common sizes include 32, 64, or 128 samples. This approach combines the computational efficiency benefits of SGD with the stability of full batch updates. The average gradient across a mini batch tends to be less noisy than SGD, leading to more stable convergence, while still being computationally efficient and able to benefit from parallel processing capabilities of modern hardware such as GPUs. As we saw, incremental and mini batch updates can be noisy because every update ends up chasing the error on the last sample of the batch. An easy way to visualize this is to use a contour plot, which is a two-dimensional representation of the loss surface. Imagine a bird's eye view of a landscape with hills and valleys. The hills are points of high loss, the valleys points of low loss. Each location on the map represents different values for our model's parameters, so we can observe the journey of the updates as they seek the lowest valley, the optimal solution. The noisy updates of stochastic gradient descent can be visualized as a path on this map bouncing around erratically, resulting in issues with convergence. A technique to mitigate this issue is momentum, which helps the algorithm keep moving in a consistent direction, smoothing out the path. This is done by computing a running average of the previous gradients. This running average acts as a memory of the direction the updates have been moving in. By combining this memory with the current gradient, momentum ensures that updates are more stable and consistent, reducing the erratic bouncing and aiding faster convergence. Another useful optimization algorithm is called root mean square propagation, or RMS Prop. Think of it as a smart break system that dynamically adjusts the learning rate of each parameter based on the historical average of the derivatives. This method ensures that parameters which receive smaller updates due to smaller gradients get a boost in their learning rate, and vice versa. This helps in faster convergence by dynamically adapting the learning rate for each parameter. The ADAM algorithm, adaptive moment estimation, attempts to blend the best of two worlds. It uses momentum to keep updates moving steadily in one direction and borrows from RMS Prop to adjust the learning rates, increasing the chances it finds a more optimal path towards minimizing the loss. This was an exciting episode. We essentially learned how multi-layer perceptrons are trained, and believe it or not, this is exactly how foundational models such as GPT-4 are trained today. Now, as usual, I'm gonna drop a link to the mind map used for this episode in the description, together with additional links that you might find useful if you want to dig deeper in the episodes that we covered today. If you found this video interesting, make sure to hit that like button and subscribe to the channel, and if you've got any questions, just drop them in the comments below.